So, hello everyone, welcome to Advanced Functions Grade 12 classes. And in today's class, we're continue to investigate properties and characteristics of polynomial functions. It is pretty interesting chapter of advanced functions because in this part, you'll learn to analyze the graph by only looking at mathematical expression, or the algebraic expression, or the equation of a graph, and the function of the graph, and we'll discover such things like leading coefficient, the greatest exponent of the polynomial functions, whether it's odd or even function. And this is what we covered in previous class. We actually already looked into some examples that you can see on the screen. We already determine the degrees of degree of a certain polynomial function, the even or odd this degree, the leading coefficient that defines which direction our polynomial function would open up, as well as end behavior that is directly related to the degree and whether the function even or odd, and of course the number of turning point, which is directly related to the degree of the polynomial functions. We haven't started any particular example yet, but I hope you reviewed this material on your own at home. And before we start solving examples now, I'm so sorry. So before we start doing examples today, I would strongly recommend you to check out the YouTube video that I'm going to show on my screen right now. Let's check out this short YouTube video and see if we understood this topic right together. This is only 15 minutes video. Let's watch it, and once we're done, we'll continue to problem solving together, and I'll be able to answer any of your questions. So I'll stop the video for a second. Here on the screen, you can see two basic methods, and basically two basic steps in analyzing polynomial functions based on their characteristics. First one is to substitute x for positive infinity and negative infinity into your polynomial function and see what is the end behavior, or in other words, what values does the function take at the end, at the ends of its graph. So to the left-hand side and the right-hand side, where the graph points. Because, for example, if the quadratic function of second power concaves up or opens up, so it means that end behavior for both ends of this polynomial function would be y travels to positive infinity. On the other hand, if the leading coefficient in our polynomial function has minus in front of it, it would mean that the polynomial function or a parabola would be open downwards, which means that the end behavior for both ends of parabola would be negative infinity for y value. And talking about when x equals 0, what is this value of y? In this way, this is when we are looking into um, so it's called y-intercept, because if you say x equals 0, then on the graph this point will pass somewhere in y-axis, so it's y-intercept. So in this particular example, you can see that here's an expression of a polynomial function in terms of product terms. And each of these products contains the sum of x with some constant value. And usually, roots of this expression when y equals 0 are easy to find, as he says, because you simply have to look when one of these brackets turns into 0, it means the rest of them will turn into 0 as soon as there's a multiplication of them. So another thing, it's really useful technique to be able to factorize your polynomial function into product of lower degree functions. Basically, here we have product of 3 functions of first degree. Let's continue. So let's clarify at this stage why when x travels to negative infinity, y points down, as well as x travels to positive infinity, y points up. And this has to do with the degree of our polynomial function. If our polynomial function has odd degree, like 1, 3, 5, then it will have a following behavior. When x travels to negative infinity, as well as y would travel to negative infinity. If x travels to positive infinity, y would look upwards. And the other way around, if we have an odd function, depending on the leading coefficient, both in x positive infinity and x negative infinity, y would be pointing same direction. So let's find out when we have, what rules do we have for this polynomial function? And first example, when y equals 0, x would be equal to 0. If you look here, x is multiple without any constant multiple or without any additional term. So simply substituting x for 0 will turn all of these brackets into 0. So this is the first root. Second root, when x equals -1, if we look into second bracket, we can see that x plus 1. What value of x should we substitute in here in order to get 0? Of course, -1. As well as for the rest of the three brackets, for number 3, x would be equal 3 because x minus 3. For number 4, we would have x equals 1 because x minus 1. And for number 5, we would have x equals -2 because x plus 2 in this bracket we have. And if you take a look into all of these roots, we have, so basically, y, so basically we're going to have x intercept when the graph passes through the x-axis in 5 different points. But if it does so, if it passes the x-axis here and then it passing it here, it means that somewhere in between those 2 points, our graph, in between of those 2 points of our graph, it had to change its direction, right? In order to get back to the x-axis and cross it. So we can say that between these roots, we're gonna have some points of local extrema and local minima. And we covered them in the previous class together. So I think this video was pretty good for us to strengthen our understanding. And let's take a look at the one more. Let's take a look at one more short video. So it is important to notice that we always read our graph from left to right, and that's how we define whether the function is increasing or decreasing at a certain interval. If the function grows from left to right, definition of a growing function is that, let's say we have x1 here and x2 here, that function f of x1 would be less than f of x2. So the next x value in the coordinate axis, so for example, x and the x1 is less than x2. In this particular case, if this inequality gets confirmed in your particular case, it means you have a growing function at a certain interval from x1 to x2. If function when x takes value x1 less than function when x takes value x2. And the other way around, if we have f of x1 greater than f of x2 and x1 is still less than x2, it means the function is decreasing this interval in the middle because the function becoming smaller when x increasing. So I hope you got a great overview of this topic, and I suggest we move on to our reading material and take a look at a few examples in here that we have. And question number 1, describe the end behaviors of each function, the possible number of turning points and the possible number of zeros. Use these characteristics to sketch possible graph of the function. And example A, we'll review only one example. So function is as follows, is -3 times x to the 5th power plus 4x to the 3rd power minus 8x squared plus 7x subtract 5. So the degree, let's break up this function and take a look at the leading coefficient, greatest power, etc. So to begin with, the degree of this polynomial function is odd. If we look at the greatest degree, it's 5. So the function has opposite end behaviors. Here we can see a notation for the end behaviors. As x travels to -infinity, y would look upwards, and as x travels to +infinity, y would look downwards. If we wouldn't have the leading coefficient -1, then we would have -infinity here and +infinity here. So, but the leading coefficient is negative, so the graph must extend from the 2nd quadrant to the 4th quadrant. And here you can understand if x is a very large negative number, such as -1000, minus 3x to the 5th power will have a large positive value and will have a greater effect on the value of the function than the other terms. Therefore, the graph will pass through the 2nd quadrant for very large positive values of x. And -3x to the power 5 will have a large negative value. Therefore, the graph will extend into the 4th quadrant. I have no questions about that. So here is our suggestion on how this curve may look. It extends into 2nd and 4th quadrants. So now, because we already know how 5th degrees of a polynomial function can look like, if we move back a little bit, we already had an example with fifth degree. You see, we have several inflection points and local minima and local maxima. I believe somewhere here, yeah, quintic means to the fifth power. And you see that these types of graph usually have lots of local minima and local extrema. So this is one of possible outcomes, but how do we know how many turning points are there? But now we have to use the behavior of the function in order to sketch the possible graph of this polynomial. As soon as it's a polynomial function of fifth degree, we can have up to 5 zeros in this function. So up to 4 turning points. And let's take a look at the final shape. All of this shape could be real, but we don't know yet because we have to investigate the graph. And here we have to investigate the algebraic function, first of all. Find the roots of this function in order to understand how many x-intercepts are there. So let's take a look at the final graph, and we can see here we have 1. I'll do the other way around. I'll use the red color and just straight line. I'll make a straight line whenever the graph is bouncing and changing its direction. We have 1 here. We have 2nd here, 3rd here, and 4th here. So you see our function has 4 turning points because it could have 5 roots. And let's count the roots. 1, 2, 3, 4, 5. So basically, since the function is a fifth degree polynomial, it must have at least 1 zero and no more than 5 zeros. And this can be implemented to any degree of polynomial function. So for example, if you have quadratic function like parabola, it could have either 2 zeros or 1 zero, but no more than 2 zeros. Of course, it also may not have any zeros, but it's only for quadratic function, because if you look at the graph, it can be positioned above the x-axis and be turning down in case if it's even function. But for odd function, we know that one edge would always jump to the other side, to the infinity plus or minus. So it will have at least 1 zero. Let's take a look at example number 2. Reasoning about how given characteristics fit particular functions. What could the graph of a polynomial function that has range y(er), where y is less or equal to 10, and 3 turning points look like? What can you conclude about this equation? So first of all, the end behavior of this function, we have to state it right away, because we see that even though y(er), its range is limited to values less or equal to 10. So it means if we're talking about polynomial functions, that both ends of this polynomial function, so both end behaviors and plus infinity for x and negative infinity for x would both look downwards. In both cases, it would be negative infinity for y. Since the range has an upper limit, both ends of the function extend downward toward negative infinity in the third and fourth quadrants. For this to occur, the leading coefficient in the equation must be negative, right? Another interesting fact, because remember, how do we get a function that, first of all, both ends are pointing to the negative infinity? First of all, it should be, I think, even degree function, plus it should be it must be having a leading coefficient negative, maybe -1 or wherever. We only care about the sign, and the function has at least 2 zeros because the function has a maximum value that is positive, and both ends extend downwards. The function must cross the x-axis at least twice. And at this stage, I believe we discovered a lot in order to plot this graph. Let's make a nice coordinate axis here and use our pen and a paper just to do that. So YER and Y less or equals to 10. So let's say 10 would be somewhere here. So we have a horizontal border on top that our function is not passing, and it's going downwards from this point, y less or equals to 10. So let's say we have point here. So if both end behavior end up in negative infinity for y, so it means the graph would look something like this. I don't know. Maybe it's a quadratic function. So it is clear as a day that when we have function value located in first quadrant or wherever second quadrant, but in positive y values, and we have to. Oh, hello, Yasser. 1 second. It's unfortunate. My screen hasn't been showing properly. Can you hear me, Yasser? Thanks for coming to the class. So I was talking about this particular graph here. Make a coordinate axis real quick again. And this is what I was representing, that we know that y value getting less or equal to 10. So we can denote it somewhere here. This is y equals 10. This is y value, this is x. And we know, in fact, that this graph starting from positive value of y would go downwards because the end behavior says so. The end behavior states that the y travel to negative infinity in both ends of the graph. And we know if at least one value of this graph located in positive values of y, in order to get to negative values, it will have to cross the coordinate axis for x. So we're going to have at least 2 zeros in this function. Here's the explanation from the book, because the function has a maximum value that is positive and both ends extend downward. The function must cross the x-axis at least twice. Is there any questions about this property, Yasser? Okay. The function has an even degree. How can we say that the function has an even degree? Because Since the function has an absolute maximum, it must have an even degree. This is confirmed by the end behaviors because they are the same. Okay, and remember, when the polynomial function has an even degree, the end behavior would be same for x positive infinity and x negative infinity, as well as having a local extrema or local maximum value. When x reaches its local maximum, as I showed on a graph, this point where x takes value 10, because it's the greatest point of the highest point of this graph, this is the local extrema. And the other way around, if we would have a graph that pointing upward, that is concave up like this, let me use other color, let's say kyan. If the graph would be concave up, we wouldn't have the local maxima, we would have a local minima. It means that basically we would have a different end behavior and the leading coefficient would be different. So many things would change. The degree of the function is at least 4. This is an interesting notation because if you take a look at the graph, I express this graph as a quadratic function, first of all. And you see that this quadratic function corresponds with the characteristics that we just mentioned. This brings us back to the part where we say there are many different graphs that may correspond to your characteristics, but they won't represent the particular function that you're trying to find. So it is not possible to be sure about the degree of the function, but the degree must be at least one more than the number of turning points. And turning points, this is an interesting part. I don't understand why they say that this function may have more than one turning point. So and let's talk about their statement that the degree must be at least one more than the number of turning points. As we discovered with a quintic function, which is a polynomial function of 5th degree, just recently over here, this polynomial function has degree of freedom, oh, sorry, not degree of freedom, but degree 5. And considering that, it can have up to 5 zeros, from 1 to 5 zeros. And it's like counting knuckles on your hand, because if you take a look at the number of knuckles in your hand and number of concavities between them, you can see that there are one less than number of knuckles, and these knuckles you can treat them as number of zeros. So the reasoning about that, if you have 2 zeros, 1 and 2, it means that somewhere between these 2 zeros you have to change your direction, and there is no other way to do it, because how else would you cross the x-axis if you are not changing your direction after crossing it? That's the simplest answer. No way. The only answer is there are going to be at least one turning point between 2 zeros. And yet for this particular case, I cannot understand. I really cannot understand why they say that the degree of this function is at least 4. Oh, this is why. Because in the problem they say the graph has 3 turning points. Okay, this explains a lot. So now, yeah, you can see 3 turning points. So we have to have at least 4 degree for this function. Yes, sir. Do you have any questions up to this moment about degrees of degrees of a function and turning points? This is very important part of this whole chapter, because based on this, yeah, of course we'll do another example. Based on this theory, you're going to analyze all the rest of the functions. Here's the summary. Please take a moment to look through it, okay, Yasser? And note down some little like key concepts in your copybook. Sorry. Just look through this core key ideas as soon as you're a little bit late to the class. Okay, and let me know once you're done. Look at these key ideas first, and then we'll move to example, okay? Read them. Oh, yes, I suggest it's really important that you read this information on your own, not just watching YouTube videos or listening to me. From my perspective, reading is the most effective way of learning. This is my personal advice to you. And I never really believed it until I tried it, you know? So please try it. And I give you 10 minutes to look through this page. Yeah, 5 to 10 minutes, read through this page, think about it, and answer any questions, and then we'll move to example. Yes, sir. How are you? I believe I gave enough time to get familiar with this summary of this chapter. Okay. I suggest we will solve a few examples. Let's do example number 1 real quick. State the degree, leading coefficient, and end behavior of each polynomial function. So, number A, change the color to black. Example A. First, state the degree. Degree equals to what? Degree is the greatest power of the independent variable in the function. And in example A, I can see that it's 4, right? So degree is 4. Leading coefficient. What is leading coefficient? Leading coefficient is a multiplier in front of greatest exponent, so x to the 4th power, and the leading coefficient in this case is -4. So leading coefficient equals -4, or it's negative, right? This is the important thing that we would like to know, that it's minus. Okay, so we already know that this function is even degree, and it has the leading coefficient minus. And end behavior of each polynomial function. So what we can say about the end behavior of this function? We know that for even degree functions, the end behavior would be similar, right? So basically same. And in this particular case, we have to look into leading coefficient. It will say to us what value will be the function in x positive infinity and x negative infinity. And I can see that my leading coefficient is minus, so arcs of my polynomial function would look downwards. So it means that the end behavior for x travels to positive infinity and x travels to negative infinity. Y would be negative infinity. It is same end behavior on positive and negative infinity for x because we have an even degree function. Yes, sir. Do you have any questions about this? I hope you have questions. Okay. Do you think we should take a look into another example from first exercise? Or you're good with degree of function, leading coefficient, as well as degree? And another one? One more, right? Let's take a look at D. It has pretty interesting shape. So degree of example D. How do we evaluate the degree in when the polynomial function expressed in product terms? So I just calculate the number of x's in all the brackets and outside of brackets, of course, too. And I see that this polynomial function has degree 4. Do you agree with me? Then the leading coefficient, we would to find the leading coefficient, we would have to look into this guy, because it's the only x that has some kind of multiple in front of it, so it will define the leading coefficient. And in this case, leading coefficient is 2, which is positive. And now end behavior for x travels to positive infinity and x travels to negative infinity. What would be the y value? And the y value would be as follows. Let's analyze. We have the even degree function, so end behavior should be similar for positive infinity and negative infinity. Leading coefficient is positive, so my polynomial function will be concave up. As simple as that. So end behavior would be positive infinity for both ends. Pastor, what do you think about it? Yeah, sir. If you mind, maybe you can use your microphone so we can communicate faster. Okay, whatever. So, any questions about defining the degree of a function, the leading coefficient, as well as end behavior? B and C is your home assignment. So please solve it now and give me your answer, and we'll analyze it together. Okay? Okay or no? Yes, sir. Do B and C, okay? So yes, sir, how's it going? Okay, so what is your answer for G? I can see the degree is 5, the leading coefficient is 2, and the end behavior would be opposite because it's an odd degree. Yes, yeah, opposite, great, and number C is also opposite. You're right, it has third degree power. So it's opposite. So, but where is it pointing? It's as soon as the leading coefficient is positive, and x travels to positive infinity, y would travel to positive infinity as well. When x travels to negative infinity, y would travel to negative infinity. And the way I try to explain it to myself, when you look at the greatest degree and the greatest power in your function, and whether the leading coefficient positive or negative, based on that, you can say what would be the end behavior, because greatest degree would also have the greatest impact into value of our function. For example, if x takes very, very big value, let's say 1,000,000. If x equals 1,000,000, you can see x raised to the 5th power, 1,000,000 to the 5th power, is much bigger than x to the 3rd power, x to the 2nd power, and x to the 1st power, all together. No, it doesn't matter even they add up, because the 5th degree would give us greatest impact into range of a function. B is going negative down. Yes, or the negative going, wait, B is going negative down, right? And C is going up, right? I see that B is going up to the right-hand side. When x travels to positive infinity, graph is going up. It will be the other way around for C, because we have leading coefficient minus. So the end behavior will basically switch. When x travels to negative infinity, graph growing, going up. And when x travels to positive infinity, y travels to negative infinity, going down. Is that what you're trying to say? Yes, sir. Going negative down. So yeah, when x travels to negative infinity, b is going down. So when the leading coefficient is positive, it means that for even an odd degree function, it would have different consequences. For odd degree function, the odd degree function will always have one side pointed to the positive infinity and one to the negative infinity. A leading coefficient only defines which side is pointing where. Yes, and since both are odd degree, and example B has positive leading coefficient, it means when x travels to positive infinity, y would travel to positive infinity as well. And when x travels to negative infinity, y would travel to negative infinity as well. On the other hand, in example C, we have leading coefficient minus, which basically gonna tell us that when x travels to positive infinity, y would travel to negative infinity. And when x travels to negative infinity, y would travel to positive infinity. Do you get what I'm saying here? Okay. So one more time, just to clarify, even degree would have end behavior same, whether it's going to be plus infinity or negative infinity for both sides. On the other hand, odd degree would have reversed end behavior. One side would go to positive infinity and the other side would go to negative infinity. Okay, hope it's clear. Let's solve a few more examples. Congratulations, Yasser, you already reduced the amount of your home assignment. So here they say determine the minimum and maximum number of turning points for each function in question 1. And let's remember, how do we determine the minimum and maximum number of turning points? The number of turning points is going to be so first thing first, we have to look at the degree of a function. If the degree of a function, let's say 4, it means that this function can have up to 4 roots, up to 4 solutions in here. So what root is? Root is when y equals 0 and x equals some value. So basically, roots are points where our function crosses the x value. If we say determine the minimum and maximum number of turning points, and we know that number of turning points would be 1 less than the number of zeros. And how many zeros can we have in this function? If this function is 4th degree, it means we can have up to 4 zeros, from 1 to 4. Okay, for this one we have from 0 to 4 because this is an even degree, and there are cases when even degree function may not intercept the x-axis, so we won't have any roots. So from 0 to 4 is the number of roots for this function, and we know that the minimum and maximum number of turning points would be 1 less than the number of roots. So we can have we're going to have at least 1 turning point and maximum of 3 turning points. At least 1, because the end behavior of this function says to us that it will be pointing to the positive infinity. This particular case would be pointing to negative infinity because we have leading coefficient minus. So if, as we described in an example, if we have some maximum value, we're going to cross, we're going to have at least 1 turning point, because if we start from negative infinity, how would we get back to negative infinity if we're not turning? So for question A, my answer is determine the minimum and maximum number of turning points. Minimum number is 1, maximum number is 3. Is that clear why it is so? Yes, sir. For example, D, we have the greatest, so the degree of this function was 4, right? We determined with 4. So again, the answer for number of turning points would be from 1 to 3. Determine the minimum and maximum number of zeros that each function in question 1 may have. And as I said, we can have from 0 to 4 zeros because the degree of this function is 4. If we would have an odd degree function, for that function, number of zeros would be from 1 to 5, let's say, because 5 is an odd number. At least 1, because odd degree functions, they start, for example, in negative infinity and go to positive infinity. It means that they're going to cross the x-axis at least once. They can cross this x-axis like this and start turning after it, but number of zeros would be single. Or it could be 5 or 4, depends on the parameters that are used in this function. So did you get the question number 2? Yes, sir. Okay. So to strengthen our understanding, let's take a look at the question number 3. For each of the following graphs, decide if A, the function has an even or odd degree, B, the leading coefficient is positive or negative. So in the first example, I can see that both end behaviors of my function are negative infinity. So it means that this is going to be an even degree function. Am I right? Furthermore, the leading coefficient is positive or negative. I know that if for even degree function I have end behavior negative infinity, it means that my leading coefficient should be negative. So my answer is my leading coefficient is negative. Did you get it? Example number 2, same example, negative infinity, pointing downwards. So negative, so even degree and leading coefficient is minus. In example 3, one side is positive infinity, the other side is negative infinity. So right away I can say this is an odd degree function. Whether it's positive or negative, let's take a look. When x takes negative values, y travels to positive infinity, and the other way around. When x takes positive values, y travels to negative infinity, which makes me to think that the degree of this, the leading coefficient should be negative. Am I right? In example 4, I have really nice quadratic function, and I can see that the end behavior is positive infinity for both ends. So I can make a statement this is an even degree function, plus its leading coefficient is positive because it's concave up. Yeah, sir. What did you say? Do you understand now? Okay, beautiful. Now practicing. This is simple. So let's do example number 5. Use AND behaviors, turning points, and zeros to match each polynomial equation with the most likely graph below. This is also part of your home assignment. And let's do one example together, and then you'll do the rest on your own, okay? So example A, 2x to the third power minus 4x squared plus 3x plus 2. Let's state that degree of this function is odd. It's 3. It's odd. Plus leading coefficient is positive, plus 2. So the end behavior of this function should be x travels to positive infinity and x travels to negative infinity. For x travels to positive infinity, y travels to positive infinity, and for x negative, y travels to negative infinity. This is our end behavior. So let's take a look at the graphs we have. We should see that right side of a graph pointing to the positive infinity and left side of a graph pointing to the negative infinity. Example D can match. Example B can also match. And that's it. No other graphs that will match. But now let's take a look closer. See, here we have a turning point. Here we don't. Here we have one turning point. No, actually here we don't have any turning points. The graph is constantly growing. We have both these examples. We have 1, 0. Now let's talk about zeros, right? How? Because we have to know where will this graph cross the x-axis in order to say that this example A is a graph B or a graph D. We have to know where it crosses the x-axis, because you can see that example B crosses in one point, and example D crosses in the other point. So I suggest, you see, y-intercept wouldn't work when x equals 0, because on the graph we cannot really say where this point is. So we're gonna look for zeros or x-intercept. And how to find the x-intercept? We have to say that this function a, which is 2x to the third power minus 4x to the second power plus 3x plus 2 equals 0. We have to solve it. You have to find when this function equals 0, right? Answer, how would you search for zeros in this function? How would you find zeros of function a? Basically, how would you solve this function? That's one of the possible solutions. So please go ahead and try to find the zeros. Yes, absolutely right. Root would be the x-intercept of this graph. So once you find the root, we would know whether it's B or D graph that corresponds to this function. Because you see, function D passes somewhere from 0 to -1, while function B passes in a range from -4 to -2. So -1 and +1. If I try substituting -1 and +1 into function, do I get y equals 0? I don't think so. If I substitute -1 into this function, I would get 2 minus 3 and -2 minus 4 minus 3 and plus 2. So -1 and +1 are not the roots. In this case, I don't really see how can you use a perfect square, but whatever. let's not waste too much time on it. I'm going to show you another interesting technique. So here they show to spend your time at home on practicing how to find zeros of polynomial functions. Okay, because it's not part of our course, but it wasn't a pre-required skill, so spend some time. And I'll show you another method right now. You see here they say use turning points. And what is the turning point? Turning point, for example, right here in a graph B, you can see, enlarge it a little bit. Yeah. Here in example B, you can see that we have two turning points, for example. Here and here. What turning point means? Turning point means the graph changing its direction. So for example, if the graph being increasing, after turning point will decrease. After another turning point will increase again. And what can we do in this case? We can compare whether the function will increase or decrease at certain interval, okay? So to compare these two functions, let's see, we already know that one of these two graphs will help us. So let's take a look at the graph in this particular range where one graph is obviously decreasing, right? In this area, in this little area, graph is decreasing, while another function is not decreasing. The other function is constantly increasing and in the same range. Same range, and you can see that the function is increasing here, right? So now let's take few values here. For example, -1 and 0. How you like that? Let's compare those two values. If we substitute x for -1 into example A, let's see what would we get. Remember how to identify whether a graph is increasing or decreasing. We are looking into the difference of the function. If f of x1 greater than f of x2, where x1 is less than x2, it means that the function is decreasing, because the least number of x gives us greater value of the range, right? So function was bigger, it turned smaller, so function is decreasing. And the other way around, if function was less and it became bigger when x equals to same way, x1 less than x2, it means the function is increasing. And let's compare these two values for function A, -1 and 0. If we substitute x for -1 into this function, we can see that we'll get -2 minus 4, so it's -6, 9 minus 3, so it's -9, plus 2, so it's -7. So y would take, when x equals -1, y would be equal to -7. That's already enough for us to determine which graph is the right one. Because look, for graph B, right? This is graph B we have here. For graph B, when x -1, we can clearly see it. When x -1, the function is positive. Function takes positive value. It's above the x-axis, but we get y equals -7. So the most probable graph would be D, because here when x -1, the range of a function is in negative value. Do you understand my method here? So this is one of the examples. So can you please do the example C on your own right now? Because it's simple quadratic function, it's easier to find roots in. So please do C and tell me your answer. So let's check it. If we substitute x equals -3, we would have 9 minus 9 minus 5. Yes, I don't understand. How? Why x plus 3 or x minus 5 equals 0? I don't agree with you. I'll show you my method while you're trying to solve it. I use the discriminant. This is the formula. I'm not sure which way you're being thought about it. So d equals b squared minus 4ac. In this case, it would be 9 minus 4 times a, it's 1, times -5, it's 20. So plus 20. So d equals 29. Now we need the square root of d, square root of 29. Let's keep it as it is. So x1 and x2 would be minus b plus minus square root of d divided by 2a. This is equals to -3 plus minus square root of 29 divided by 2. This would be our two roots for this function. We can approximate it. The square root of 29. Let me use the calculator. So, where is it? 29 and square root of it would be 5.385. Something like that. So it would be -3 plus minus -3 plus minus 5.385 divided by 2, which is equal to roughly 1. First root, when we add up, first root would be somewhere around 1, and second root, when we subtract, would be somewhere like 4.1925, but negative value. So if you take a look into the graph that we have here, first of all, this is a odd degree, even degree function, right? Square. Secondly, the leading coefficient is positive, so it will be concave up. It will be looking upwards in both ends. And there are two functions like that, c and e. But we already found our two zeros, right? Somewhere around 1 and somewhere around -4.1925. And I can see that these zeros are present on the graph E, here and here. So I would make a statement that the C has graph E as the most probable graph. Yes, sir, do you agree with me? Perfect. So the rest of these problems, I leave it for your home assignment. Mm-hmm. Mm-hmm. Can you use annotation in on your PC if you're connected through the PC? Can you draw on the desk? Okay, wherever. Let's do example 12 together. The graph of a polynomial function has the following characteristics. Its domain and range are a set of all real numbers. So let's write it down. D E R, right? D E R. Range E R, right? Because the domain and range are set, these all are the set of all the real numbers. Okay, they're turning points at x negative 2, 0, and 3. So x equals negative 2, 0, and 3 is going to be a turning point. And question A, draw the graph of two different polynomial functions that have these three characteristics. B, what additional characteristics would ensure that only one graph could be drawn? Let's make A. And I would like you to answer the question B. What additional characteristics would ensure that only one graph could be drawn while I'm sketching these graphs? So I'll do it right here. This will be graph number A. This would be graph number B. So first of all, I'm looking for, yeah, its domain and range is set of all real numbers. The turning points are at x negative 2, 0, and 3. So x0, let me use another color, let's use black. So x0, x0, negative 2, negative 2, and 3. Negative 2, and 3. And then let's return back to the question. The graph of a polynomial function has the following characteristic. Its domain and range are set of all real numbers. So it means there is no limits in x or y axis. So I can make a statement that my polynomial function will be an even degree, or sorry, it would be an odd degree because it's not limited to certain range. Am I correct? So it's going to be an even degree. Okay, and we have 3 turning points. So it means that the degree of this function is at least 5, because the number of turning points, maximum number of turning points is 1 less than the number of the degree of the function. If we have 3 turning points and we made a statement that this function is an odd degree, so the nearest odd degree that we can use is going to be 5. So I would say that I can have up to 5 zeros in this function. But I'm not sure for 100% how many degrees in this. I know for sure that it's odd and that is 5 or greater. You got it? It's 5 or greater. So let's make a drawing. If we have a turning point and -2, let's say I start from positive infinity, I go to 2, I change direction. Now I have turning point at 0, I change direction again. Now, wait. I'm kind of confused right now because it says that its domain and range are set at the set of all real numbers. Meanwhile, there are 3 turning points. And if we have 3 turning points, it means that no matter how hard we try, we will end up in same infinity region, whether it's going to be plus or minus. So I made a mistake. This is not an odd function. This is most likely an even degree function because we have 3 turning points. It's like turning left, right, and then left again, right? You cannot go to the negative infinity if you start from the positive infinity. If you made 3 turns, you're returning back if you made odd number of turns. So this is one possible graph of this function. And the second possible graph, why wouldn't I start it from negative infinity? Again, turning point here, and let's say turning point. You see, I sketched 2 graphs of a polynomial function that both correspond to the given characteristics. But how can I define what additional characteristics would ensure that only one graph could be drawn? Yes. What else do I need to know in order to make a graph that is 100% the polynomial function I'm describing? Take notice, characteristics, not only one characteristic, there's several of them. What would you say, Yasser? Which characteristics do we need? I just showed you an example how we can end up in positive infinity or negative infinity without additional characteristics. This already hint for one of the possible characteristics that we need. Yeah, sir, it was me. Oh, okay. If it said if the leading coefficient is positive, yes, that's one of the characteristics. Great job. And one more. Remember, we've been investigating the zeros of the function. Because right now I can draw in one more function that will correspond to the criteria. If you look here, I can go up to here, then turn here, then turn here, then turn here. And I'll have much more zeros. Not exactly, because Oh, so what you're saying is, if we would knew how many zeros do we have, then we could make it, because, for example, if we knew that it has only 1 0, this purple graph wouldn't fit, right? If we knew that we have 2 zeros, this graph wouldn't fit. Or what are you trying to say? Okay. Yeah, definitely. Definitely would need to know how many times does the graph crosses the x-axis, because when we don't know that, we can make a graph where we don't even cross the x-axis, where we don't have any zeros, and then it would be two different polynomial functions unless we know that. Great job, Yasser. I'm proud. I'm proud that you came up with the solution on your own. So feel like we covered pretty much in this class. Let me clear the drawing. And I will give you to try this problem, where problem 14, and it will be a final problem for us to do. Let's read it together. F is a polynomial function of degree n, where n is a positive even integer. Decide whether each of the following statements is true or false. If the statement is false, give an example that illustrates why it is false. So, Yasser, please take 5 to 10 minutes to look through this problem, and then we'll discuss it together. So Yasser, are you ready? I'm not sure how can you answer me in text form because it's going to be quite lengthy. So I hope you came up with your own solution. I'll tell you mine. Please just confirm whether it's similar to yours or anyhow different, okay? So I hope you can hear me. An example in question A is f is an even function. Let's read the question one more time. F is a polynomial function of degree n, where n is a positive even integer. Okay, so we know that the greatest power of this polynomial function would be n, and it's even. And question A, f is an even function? Not exactly. We cannot say that the function is even unless we have symmetry over the y-axis. Only the functions that are symmetrical over y-axis can be called even. But in this particular case, we don't know for sure whether it's even or not, because even if f of x equals x to the power n plus something, this something could contain x to power 3, for example. And this is not an even power. So it is not even. Great answer, yes, sir. This is an example when this function would be neither even or odd. Question B. F cannot be an odd function. And that's true because considering what we just discovered in the first question, f cannot be an odd function because the greatest power of this of this function is n, which is an even integer. So there is no way for us to make this function odd. So this is true. So we don't have to give any illustration. C, f will have at least one zero. This is false statement because we know that this function is even, so it means that the end behavior for this function should be same. Sorry. Yes, sir, you say A is true? No, A is false because even function could be only if we have symmetry over the y-axis, remember? And you were right, absolutely. But even though this degree is positive, is even, it doesn't mean that the function is even, okay? Because here's an example where we have n, which is an even integer. So this is an even degree, but as soon as we have x to the third power or x to the fifth power, x to any odd power in this function, it will make this function neither even nor odd. Okay? Considering the same logic, B is true because f cannot be an odd function. And the question C, f will have at least one zero. If we know that this function is even, it means the end behavior for positive and negative infinity for x would be the same. So in both ends of this function, it will point either upwards or downwards, which means that we shouldn't necessarily have at least one zero because our function can be completely located in one quadrant, right? Whether it's up or down. So we won't have any zeros. If it's not even, then shouldn't it be odd? No, because we have a case when function neither even and nor odd. Okay, if the function odd only if we have all the odd powers for x. If you remember, before this, let me scroll up. We had an example of neither we had an example of function that wasn't odd and wasn't even. Here, you see, even though this function is even, and not the, but the degree of this function is even, it is not even function. And it's not odd function as well. And your question, if it's not even, then why it's not odd? Because it's not odd because in the question it says the degree of this function is n, and n is a positive integer. Then how? Oh, sorry, I thought it says n is even. Just give me a second. I thought it says n is an even degree. It just says that it's positive. Okay, so considering this fact, A is false because we don't know what integer is n. It could be positive or negative. Question B, f cannot be an odd function. This is false. F can be an odd function if n is an odd number. Okay, and if we don't have any other even degrees in the function. So question B is false. F can be an odd function. And question A is false. F could be not an even function. Now it's clear? Okay. The question C. Wait, so how did I miss that? It says even integer. You see, it says even integer. I missed, I don't know, I just got a blurry eye or something. So yeah, first time I was explaining it right. F is an even function is false because it could be neither even or odd. And question B is true because f cannot be an odd function because n is an even integer. Okay, now it should be clear. Yes, sir. Function cannot be, I'm sure, I'm 100% sure, because for some reason I didn't see even second time. So it says that n is a positive even integer. If we have an even power in our function, it means the function cannot be odd. The degree of this function is an even number. How can it be odd? Do you agree with me? Question C, f will have at least one zero. My answer is this is false because as soon as it's even degree power, even degree function, it means that it's going to end up in same infinity, whether it's positive or negative. So we can position this function in one of four quadrants completely, or even in two quadrants, but it still won't have any zeros. Is it clear? Or should I make step back to question B and A? Explain it one more time. So just to summarize, in question it says, degree of function is n. Degree is not the same as definition of a function as even or odd. You should have an even degree of a function in order for this function to be even. Okay, but there is also extra requirement. There shouldn't be any other odd degree in this function in order for it to be even. You can have an even degree, but the function is not even, as well as with odd degree. You cannot have an odd function if your degree is not odd. If it's even, the function cannot be odd. Question C. We'll have at least one zero. We explained that because our function is even degree, it will end up in same infinity, whether it's plus or minus. So we can position it in such way that we won't have any zeros. Question D. As x travels to infinity, y travels to positive infinity. As x travels to negative infinity, y travels to positive infinity. And again, this is false statement. This is we can also have y travels to negative infinity, right? It's not necessarily only positive infinity for y, because we don't know the leading coefficient. It depends on the leading coefficient, mainly which direction will this even degree function look to. Is it clear, Yasser? Is this question completely understandable now? Great. Dave, I already stole 6 minutes from you. Thank you for joining today's class. I appreciate it. I hope you learned something new, and please check out your Zoom and Google Classroom regularly.